Aloha BioChem. This video begins Chapter 7 on solids, liquids, and gases. In this lecture, we discuss gas properties. Hello again. A new chapter, Chapter 7 on gases, liquids, and solids. Lots of cool stuff in this chapter. We'll spend quite a bit of time on gases, but before we look at the outline, let's see what this guy's doing. We got a diver, looks like a couple divers. He's swimming down, and I don't know what that thing is, but I wonder if he's going to put his hand inside there. Looks like it might gobble it up. Anyway, let's see, gases, liquids, and solids. He's swimming through the liquid water, breathing gas and a bunch of solid material down here. It says scuba divers must carefully plan the depth and duration of their dives to avoid the bends, a dangerous condition caused by the formation of nitrogen gas bubbles in the bloodstream. That's right. When you're at the bottom of the sea, the pressure due to the weight of the water that you're under is squeezing your body to death, and you have a limited time in which you'll survive, and it affects your biochemistry as well. So when you're breathing in air from the tank, the nitrogen component of the air is being squeezed into your bloodstream more at the bottom of the sea, and so you got nitrogen dissolved in your blood. When you swim back up to the surface, your body doesn't experience as much pressure now, and that nitrogen can come out of your blood, and it can form bubbles in your blood, and that's very dangerous, and it's called the bends. Very painful, and it can even kill you. So lots of issues involving gases when you dive. So be careful out there. Other threats are involved when you free dive, a little bit different. So anyway, let's take a look at the outline. Several sections are spent on gases. We will recall the states of matter first. Some of that will look familiar. Then we will discuss gas properties and gas laws. As boring as the gas laws sound, they're actually pretty cool. After the gases, we quickly get into liquids and solids. Intermolecular forces are pretty important, so we'll do a lecture on that. And we end the chapter with phase changes, calculations involving phase changes. Let's go over to the notes. So here we go. Here's a consolidated list of the topics that we just mentioned. And this diagram right here might look familiar. We had a very similar diagram in Chapter 1, and it's been expanded ever so slightly right here. If you recall back in Chapter 1, I think the second lecture, we divided all of matter into these three categories. All of the material that you see around you can be placed into one of these categories: solids, liquids, and gases. And these are all different from each other. Here are some distinguishing properties. Solid materials have a fixed shape. They're rigid, they don't change their shape. Liquids and gases, on the other hand, have variable shapes. Liquids take on the shape of the bottom of their container, and gases expand to fill their container, so their shape is the shape of the entire container. Solids and liquids both have a fixed volume. You cannot really compress either one into a smaller volume. It's very difficult to do that. But gases are easy to compress. Gas molecules or particles are far apart, and it's easy to press them into smaller volumes or allow them to expand to larger volumes. The density of solids and liquids is much greater than the density of gases, and that's because of the particles. The solids and liquids, the particles are packed closer together. They're almost right on top of each other, so they're much more dense. They're heavier than gases are. Gases, the particles are far apart, so gases are much lighter. So there we go with the particles again. But another thing about the particles is in the solid phase, the particles are ordered. They're nicely lined up, one after the other, a very nice three-dimensional arrangement in the ordering of the solid particles. Liquid particles, although they're close together, they're kind of just randomly surrounding each other, and that's because they're moving around. So there's no fixed, rigid ordering in the particles. They're disordered. Gas particles are, of course, disordered, and they're very far apart from one another, so very disordered. They're flying around, whizzing around in three-dimensional space. Now, the reason solid and liquid particles are close together is because there is a certain sticking force that we'll talk about in this chapter. Particles, whether they're atoms or molecules or ions even, interact with one another. They stick together, and that's what holds the particles in solids and liquids close together. So the sticking interactions are very important for the solid phase particles. That's what makes them line up, together. And in the liquid phase, they're still close together, although they're sliding around relative to each other. The sticking force still holds them together, but the sticking interactions are not really important for the gas phase particles. They're flying around independently of one another, and they're moving too fast for any sticking interaction to be important. As an example, let's take a look at the three different phases of water. And for this example, I have a nice little diagram. Let me pull that up. There you go. Solid, liquid, and gas phase. Maybe I can move this right on top there. Solid. So you got solid, liquid, and gas. Okay. So here's solid water. You can see the molecules of water are nicely lined up in all directions. The interaction forces between the particles are holding them in place. And liquid particles are also close together, but they're sliding around. That's why liquids flow. Gas particles are far apart. Let's consider what happens when phase changes occur. If you have a solid piece of ice and you want to convert it to liquid water, you have to heat it up. So you take the piece of ice out of the refrigerator, and the environment provides heat, and that allows the solid to melt. What you're doing when you warm up a substance is, of course, it's increasing the temperature, but remember, temperature is just a measure of molecular motion. So as you increase the temperature of that solid ice, these water molecules, imagine them vibrating around more quickly, and eventually they're going to be vibrating around so quickly the temperature is going to be high enough that their vibrational motion causes them to overcome that sticking force, which is locking them in place, and so the water molecules will begin sliding past one another because they just have too much vibrational motion, and that's when melting occurs. If the substance absorbs more heat, then these liquid water molecules will be vibrating even more quickly, and eventually the vibrational motion is enough to overcome the sticking force entirely, and the molecules will separate from each other, and you'll vaporize the substance into the gas phase. Heating up a gas just causes the molecules to whiz around that much more quickly. Cooling the substance back down causes the gas molecules to slow down, and eventually they're moving slow enough for the sticking force to take over, and the substance collapses or condenses back into the liquid phase. And if you cool the liquid down, you're slowing the molecules down, and the sticking force really takes over, and it freezes back into the solid phase. Hopefully this picture helps you, and also that explanation of temperature and adding heat or taking it away. So when a substance absorbs heat to go from solid to liquid to gas, that's the endothermic direction. So going in this direction, the substance absorbs heat. Going in the other direction, heat is removed or the substance releases heat. So this is the exothermic direction. Try to remember that. If you see an example on a quiz which says solid water converts into liquid water, is that an endothermic or an exothermic process? Well, to take a piece of ice and melt it, it needs to absorb heat. That's an endothermic process. Going in this direction is endothermic, the other direction is exothermic. Okay, what's next? Now, in this chapter, we'll spend quite a bit of time on the gases and a little bit less on liquids and solids. Let's begin. Let's focus on gases. And let's consider really any gas. So here's gases. Let's consider any gaseous substance. So imagine you have a gas that's trapped inside some container, and you'll see pretty soon that one of the things that we like to do with gases is mess around with the volume. So suppose we have the gas, it doesn't matter what gas it is, trapped in a cylinder, and we're able to move the piston up and down to change the volume of the gas. Maybe we want to squeeze it, or maybe we want to let it expand. With this gas, we can ask, what sort of properties are we interested in? And it turns out that there are 4 gas properties that we'll be interested in. And they are the pressure, the volume, the number of particles of gas, and the temperature. So those are the 4 gas properties. The pressure we'll talk about in just a little bit in more detail, but it's measured using certain devices, and it can be measured in units of atmospheres or millimeters of mercury or pounds per square inch, PSI, or pascals, and there are other units as well. The volume is pretty familiar, and we can measure how many liters of gas we have, or milliliters, perhaps cubic feet or cubic meters as well. The number of particles in chemistry we almost always count by the mole, and the temperature, we've discussed a few different temperature scales, but it turns out the Kelvin is the most important one. In fact, for all 4 of these properties, I've parenthesized the units that are of the most importance for us in this chapter. Before we go any further regarding these properties, I just need to spit it out what the most important concept is in the chapter. Suppose you have a gas and it's trapped inside some container, and you're able to measure these 4 properties of that gas. And you measure the properties using these units. So you measure the pressure in atmosphere, the volume in liters, the number of particles in moles, and the temperature in Kelvin. If you take those measurements and you calculate the following fraction, the pressure times the volume over number of moles times the temperature, then you will get 0.0821. That will be the answer every single time. It doesn't matter what the gas is, where it is. If you measure these 4 properties and you calculate this fraction, this will be the answer. And that's a remarkable fact. The result is always the same. And this number, 0.0821, we call the gas constant. It's given the symbol R, and it's called the gas constant. And this equation right here is called the ideal gas law. You'll see it written as PV equals nRT a lot. So PV equals nRT is the ideal gas law. It's a remarkable equation. And in the next lecture, we'll see how it's used. So let's go back and talk a little bit more about these properties before getting into the gas laws. 3 of the 4 properties are easily measurable: the pressure, the volume, and the temperature. So let's start with the temperature. You're pretty familiar with temperature, and you probably know how temperature measuring devices work, but I'll remind you what we discussed in chapter 1. Here's figure 1.8, which shows 3 temperature measuring devices: a Fahrenheit, Celsius, and Kelvin thermometer. And they're lined up, so the Fahrenheit temperature is the same as the Celsius temperature, same as that Kelvin temperature. So kind of a cool diagram. Let's just look at the Celsius thermometer to see how thermometers work. What it is it's a glass tube that's sealed on both sides. Down here there's a pool of mercury, a little ball of mercury, and then that mercury is allowed to travel up a skinny portion of the tube right there. And it's well known that liquids expand when they're exposed to hotter temperatures, and they do so predictably. The way you make a thermometer is you immerse this part in some freezing water. Water freezes at the same temperature every single time. So when you immerse this part into freezing water, the mercury contracts, and so the mercury goes down, it levels off somewhere, and you put a little line on the glass that represents freezing water. And then you take the thermometer and then you plunge it into boiling water. That's hotter. Water boils at the same temperature every time, and the mercury expands now, and it goes up there, and you mark another little line. And now you got 2 lines which represent freezing and boiling water. And then you draw 100 equal intervals between them. And that represents the 100 Celsius degrees that it takes to go from freezing to boiling. And if you want hotter temperatures indicated on the thermometer, you just put more equally spaced intervals above the boiling temperature, and you can do the same thing below 0. And once you have your Celsius thermometer, it's pretty easy to make another one for Fahrenheit or another one for Kelvin. So that's how thermometers work. And once you have a thermometer, you can measure the temperature of a gas pretty simply. What about volume? Volume is self-explanatory. We need not talk about it. It's simple to measure the volume of a gas. It's simply the volume of the container it occupies. Pressure, on the other hand, requires a bit more explanation. It's a new type of measurement that we haven't really discussed. So let's talk about it a bit. Remember, if you have a gas, the gas fills its container, and those gas molecules are whizzing all about the container. It's possible to compress a gas into a smaller volume or let it expand into a larger volume. Now, suppose you have a gas that's squeezed inside some container, and you want to measure the pressure. So what is pressure? Well, pressure is simply a measure of how hard it is to squeeze the gas into that container. The more gas you cram into a container, the harder it is to squeeze in there. And so if you have a pressure gauge and you stick it in the container, it registers how squeezed in the gas is. So here is a pressure gauge. Let me show you one of these. There you go, a typical gas pressure gauge. And this can be screwed into an adapter on a gas cylinder. And once you screw it in, the gas is allowed to travel into a little tube right here and into the gauge itself. And the more gas you have squeezed in the cylinder down there, the more it's going to want to escape and go up into the gauge. And that causes the needle to go up and read how many PSI, for instance, is registered. I'll show you the inside of a pressure gauge. Got a little animation here. So here's the inside of a pressure gauge. This part right here represents that part right there going down, and when gas goes up into the tube, there's a circular tube that goes around. So let me show you this again. You see gas goes in the tube and it fills up this circular tube that goes around. Now, the more the gas is trying to escape the cylinder, the more that's squeezed in the cylinder, the more it's trying to escape. And what happens is this. You see that little narrow circular tube kind of expands, and through some kind of mechanism of gears over here, that causes the needle to move up. So you can't quite see how those gears work over there, but basically the expansion of this as the gas is filling it up causes the needle to go up, and that's how the pressure is measured. Pressure is, I like to think of a gas as always pushing on the walls of its container, and pressure gauges measure basically how much that pushing is. And that's a little bit more on the three gas properties. The number of moles, that fourth property, N, you can get if you know these three. So if you measure these three properties of gas, you can get the moles for free by using the ideal gas equation, which we'll talk about in the next lecture. Now, these gas properties are actually explained by the kinetic molecular theory. The kinetic molecular theory is a set of principles that explains why gases exhibit these properties. It basically says what's going on behind the scenes. It tells you what the molecules of gas are doing and why we have these properties, or why gases exhibit these properties in the first place. So let's read through these statements and see if we can see where the pressure, volume, and temperature come from. The kinetic molecular theory is a set of statements. The first one says, a gas consists of particles, atoms or molecules, moving about randomly and rapidly. Okay, gas molecules or particles are whizzing about. The size of gas particles is tiny compared to the space between them. Okay, so in any region of space, which is a gas, most of it's empty space. The gas particles are very small compared to the container itself, and there's a lot of space between the particles. 3, the gas particles exert no attractive forces on each other. So there's no sticking force, which is causing the gas to collapse into a liquid, for instance. No attractive forces. 4, the kinetic energy of gas particles increases with temperature. Remember, kinetic energy is energy of motion. What this statement means is that if you increase the temperature, the gas particles move more quickly. And 5, when gas particles collide with each other or a wall, they rebound and travel off in new directions. So you can see the temperature right here. The temperature is a measure really of how fast the gas particles are moving. And if you go back to that thermometer, where's that thermometer? When you put the mercury end of the thermometer in boiling water, those water molecules are jostling around real quickly. They're at a hotter temperature. And so what that does, that causes the glass itself, those particles, to jostle around more quickly. The water, the boiling water, energy gets carried through the glass and through into the mercury. So basically, fast-moving molecules in the water bump into the glass molecules, causing them to vibrate more quickly, causing the mercury particles or atoms to vibrate more quickly, and that causes them to spread out, which causes it to go up the glass. Hopefully you got all that. That's what's going on behind the scenes with temperature. Now what about volume? Gases expand to fill the volumes of their container? Well, we can see that in statements 1 and 2. Gas particles are whizzing about randomly and rapidly, and they're tiny compared to the space between them. So gas molecules and particles are going to whiz about and fill up their container. So there you go, volume. Pressure. The reason gases exert pressure is because they're constantly colliding on the walls of their container. And statement number 5 says, when gas particles collide with each other or a wall, they rebound and travel off in new directions. So if you have a sealed container with a gas, the gas molecules are constantly bouncing off the walls of the container. They're trying to escape. They're pressing out on the walls. And if you put a pressure gauge on top, they're gonna escape that way and go up into the gauge and exert a pressure. So this theory, these statements tell us what's going on behind the scenes, and hopefully that makes these properties make a little more sense to you. Now, a bit more on pressure. Pressure is defined, actually, let me get rid of this over here. Pressure is defined as force over area. When a gas particle collides with another particle or with a wall, what happens is it pushes on the wall with a tiny bit of force. And if you are able to measure that force, measure how many pounds it is, and divide that by the area on which the gas is hitting, then you can calculate the pressure. Let's consider this gas cylinder over here. This is going to be in the next problem, but this is a cylinder of carbon dioxide. Imagine, say, this is filled up with a lot of gas particles, and let's just consider a 1 square inch portion of the walls of the container. So we're just looking at 1 square inch. Now there's millions of gas particles hitting that square inch constantly, and the sum force that they're pushing on that little 1 square inch, say, is 10 pounds. So that 1 square inch constantly feels a force of 10 pounds. Well, you take that 10 pounds and you divide it by the area that it's acting on, 1 square inch, and that would be 10 pounds per square inch, or 10 psi. And psi is a unit of pressure. Now, if it's hitting the square inch over here with 10 psi, then it's also hitting every other square inch with 10 psi, because the gas particles are mixed evenly, so pressure is the same all throughout the cylinder. Now, if it's hitting 1 square inch with 10 pounds of force, then if you have 2 square inches, there would be twice as many gas particles. It would be 20 pounds of force. But then 20 pounds of force divided by 2 would be 10 psi. So really, pressure, it doesn't matter what size of the container walls you're examining. But that's the definition of pressure. We're not really going to use this equation too much, but just to give you an example of a calculation, let's just suppose we want to know about the pressure in a tank of CO2, and we are looking at a 2 square inch portion of the container walls. And suppose we're able to measure the force that the gas molecules are colliding the wall with. Maybe we open this cylinder up, we put a little miniature scale in there that's kind of like a pressure gauge, which measures the force. And it's a 2 square inch scale, and it's registering 1,710 pounds of force hitting that 2 square inch scale. So that's what's going on. What is the pressure of the gas? Well, you take force over area, 1710 pounds divided by 2 square inches, and the numbers give you 855, and the units give you pounds per square inch, or psi. So that's psi, units of pressure. But there are other units. You have the atmosphere unit, which is used in weather a lot, millimeters of mercury, which is also used in weather and medicine as well. And then pascals is used a lot in science. So these relations tell you how to convert from one unit to another. the millimeter of mercury, let me show you a little bit more about that. I got a barometer right here. The way a barometer works is you take a pool of mercury and it's open to the atmosphere. So the air that we're breathing is the atmosphere. You have a pool of mercury and there is this glass tube which is sealed on this side, but it's open on the bottom. So the mercury is able to go into the tube if it wants. And further, up here at the very top of the tube, the air has been sucked out. So there's no air inside the tube. There's air outside, it's open to the atmosphere, but no air inside the tube. Now what happens is the atmosphere, the air around us, the air molecules are constantly moving around and they're hitting the surface of the mercury down here. They're pressing down on the surface of the mercury and they cause it to go into that tube and up. And on an average day, the mercury goes up about 760 millimeters. That's about 3/4 of a meter. So that's on your average day, the pressure of the atmosphere. The atmospheric pressure, we say, is about 760 millimeters of mercury. And other days might be slightly higher. Those are your nice sunny days. Some days the pressure is slightly lower than 760. You might expect rain on those days. This isn't a course in weather phenomena, but weather is very much related to atmospheric pressure. But on average, the atmospheric pressure is 760 millimeters of mercury at sea level. And we call 760 millimeters of mercury 1 atmosphere. So 760 millimeters of mercury, that's called 1 atmosphere. 1 atmosphere, which is equal to 14.7 psi, and 760 millimeters of mercury is also equal to 101.325 pascals. You see pascals in science. Let's do a simple pressure conversion problem. Suppose we got a scuba diver who begins a dive with a tank of compressed air, and the air is filled with 3,000 psi of pressure. So air, by the way, is a mixture of gases. You got nitrogen and oxygen in the air. But overall, there are 3,000 pounds per square inch of pressure inside the tank. Convert this pressure to atmospheres and millimeters of mercury. To do the conversion, we need the relations above. So starting with the 3,000 psi, 14.7 psi is 1 atmosphere. You see the units canceling, you're left with atmosphere, and the calculation gives you 204.08, which rounds to 204 atmosphere. To get to millimeters of mercury, take your 3,000 psi, and we know that 14.7 psi is 760 millimeters of mercury. The psi units cancel again, leaving you millimeters of mercury, and the calculation ends up rounding to 155,000 millimeters of mercury. So that's how you do pressure conversions. Now, to end the lecture, we will talk about one of the important applications of pressure, but it's concerning liquid pressure. Liquids also exert pressure, and the way it works is by similar concepts. It's called hydraulic pressure. So you should note that liquids are pushed through a tube by what's called hydraulic pressure. So here's a tube and it's filled with some liquid, maybe that's oil, and imagine you have a piston which is pushing the liquid through the tube, and the push is called hydraulic pressure. Imagine you're pushing, the cross-sectional area is 1 square inch and you're pushing with a force of 100 pounds. Then that's 100 pounds divided by 1 square inch, or 100 psi of pressure. So that's hydraulic pressure when you push something through a tube. Hydraulic pressure has important applications. That's how a hydraulic jack works, and that's also how the heart works as it pushes blood throughout the body. Let's take a quick look at a jack. Let me find my jack. Where's my images? Here's jack. There you go. So here's your tube in gray, and it's filled with some oil. Now, this piston right here is connected by a rod to a lever, and if you press this lever down, if you apply effort here, that's going to move the piston, it's going to push the oil, and it's going to raise the load. So let's see how we can lift heavy objects. When we push down, say with 10 pounds of force, and suppose the cross-sectional area is 1 square inch. You take 10 pounds divided by 1 square inch, that's 10 psi of pressure that we're pushing the fluid with. Now that 10 psi of pressure is the same all throughout the fluid, just like it is a gas. And you have 10 psi acting on this larger cross-sectional area over here. Suppose this is 10 square inches. So you have 10 pounds per square inch applied all throughout these 10 square inches. So if you divide those 10 square inches into each square inch, this little square inch gets 10 pounds, this little square inch gets 10 pounds, and all 10 of them get 10 pounds. It's 10 pounds per square inch. And that totals up to 100 pounds of force that is lifting the load. You can imagine that you can lift very large objects. Imagine if this were not just 10 square inches, but if it were 1,000 square inches. You would need a lot of oil, and it would just lift it a little bit at a time, but you could do it. So that's how hydraulic jacks work. The heart is another application which is quite interesting, and I'll show you how the heart works. This is in figure 7.3. So the heart is like a pump. Oh, let me get rid of this picture. The heart is like a pump, kind of like a piston, I guess. So what happens is the heart fills with blood, and then when it squeezes, it sends the blood all throughout the body. So when it grows again, it fills with new blood, which comes from the veins, and then when it squeezes, it sends that blood through the arteries throughout the body. So you have the heart relaxations and contractions, and that's the circulatory system. As the heart squeezes, it, through hydraulic pressure, sends the blood all throughout the body, the artery tubes. And it turns out that higher pressure as it's squeezing is called the systolic pressure. As the heart relaxes, pressure is not as great, and that's called diastole, or the dystolic pressure. So when a patient's blood pressure is taken, normally you get two values. One is for the heart contractions, and the other one's for the heart relaxations. And the units are normally in millimeters of mercury. So let's take a look at an example problem right here involving blood pressure being taken. A patient with hypertension has his blood pressure measured at 150 over 100. That's pretty high. Now, you're not given the units here, but if you work in medicine, you know that's millimeters of mercury. So everybody knows it's millimeters of mercury. The units are implied. So you got two numbers, the systolic, higher pressure for the heart contractions, and the diastolic, lower pressure for the heart relaxations. Let's convert both of these to PSI. We know that 760 millimeters of mercury is 14.7 PSI. So we'll just convert the two, one after the other. For the systolic pressure, you take your 150 millimeters of mercury and you multiply it by the conversion factor. Millimeters of mercury on the bottom, PSI on the top, the units cancel, you're left with the proper units, and the calculation gives you 290 PSI. For the diastolic pressure for heart relaxations, it's 100 millimeters of mercury, the same conversion factor, and the calculation gets you 1.93 psi. So if you work in a clinic and you are asked to measure the blood pressure of a patient, next time, let's see what happens if you report it in psi. It's 2.90 over 1.93. See if they, no, don't do that. But interesting to see the psi conversion. So that does it for gas properties. In the next video, we will take these properties and see how they have interesting relations between them. If one of the properties of a gas changes, then the other ones change predictably. And this gives us what are called the gas laws. So a pretty cool lecture coming up. Stay tuned for that. Aloha.